So the last bit of this chapter where we talked about moles involves a stoichiometry. And you'll be seeing as we go through all these examples involving stoichiometry that we're going to be doing the same set of calculations, same pattern, just different numbers. So when we go through every example, hopefully you'll notice that we're doing the same process. It's just changing the numbers. And so with stoichiometry, there's a few key core aspects that we look at. And so one thing is we have to determine the limiting reagent. So the limiting reagent is the one that gets all used up in a reaction. So sometimes in a problem you may see keywords like excess of a particular reactant. That would indicate that the other reactant is the limiting reactant. But sometimes it'll give you both the amounts of both reactants, and you'll have to determine which one is the limiting reactant. So the one that gets all consumed in the reaction. So always you want to make sure that you have a balanced chemical equation, because that's how we're going to get the conversions between a reactant to a product or product to reactant. We get our conversion factors from the balanced equation. So you always want to check if it says unbalanced in the problem, make sure you balance the equation first and then continue. The second step is regardless of what your reactants are in, so for stoichiometry beginning with it'll be in mass, so we need to convert the mass to moles. But when we go to the next chapter, which deals with solutions, maybe instead of mass, it'll give you the amount of reactant in concentration and volume. Regardless of what your reactants are given as, you have to always convert them to moles. So the first thing you're going to do is you're going to convert in this case, the mass of reactants into moles. Then using the balanced equation, we're going to convert the reactants into a product. Now, if it tells us a product, then we pick that product. If it doesn't tell us a product, then we can pick one of the products, just be consistent with both reactants. And then once we determine the moles of product produced by each reactant, the one that produces the smallest amount of product is our limiting reactant. So then what we do is we take the moles of product produced by the limiting reactant and convert it to grams to get what's called the theoretical yield. Now, an extra step may be that the problem may ask how much of the excess reactant is left over. So based on the amount of product produced, we can calculate how much of the excess reactant is left over. And these are going to be the core steps that we do every time in this lecture. Have a balanced equation, convert mass to moles, convert moles of reactants to moles of product. Which one produced the smallest amount of product? That's our limiting reagent or reactant. And then we can find the theoretical yield of it. Then another part could be how much of the excess reactant is left over. So we got all those types of examples that we're going to show you. So here we have a stoichiometry problem. It gives us the balanced chemical equation. It gives us the molar masses of our reactants and products. And it says calculate the mass of aluminum sulfide that is produced when 50 grams of sulfur reacts with excess aluminum. So anytime you see the word excess before a reactant, you can disregard that reactant. So what this means is that there's more than enough aluminum to react with all the sulfur. So in this case, sulfur is the limiting reactant. So that's going to get all used up. Now the mass of aluminum sulfide that we calculate is referred to as the theoretical yield. So if we were to do this reaction perfectly with 50 grams of sulfur and excess aluminum, how much aluminum sulfide can we produce? And so what we're going to do is I'll write a little flow chart. We're going to take the mass of aluminum sulfide, convert it to moles of aluminum sulfide. Excuse me, not aluminum sulfide, my bad, sulfur. And once we get moles of sulfur, then we're going to use the chemical equation to convert it to moles of aluminum sulfide. Once we have moles of aluminum sulfide, then we convert it to mass of aluminum sulfide. So these are the steps we're going to do. So now I'm going to draw my train tracks. And we're starting with mass of sulfur. So we put that here. So in the first step, we're going from mass of sulfur to moles. So the molar mass of sulfur is 256. So that means it's 256 grams per mole. So the 256 goes on the bottom. The mole goes on top. So now we've converted to moles of sulfur. Next, we need the mole ratio between sulfur and aluminum sulfide. And so for that, we have to look at the coefficients in front of the balanced chemical equation. So there's a 3 in front of sulfur and an 8 in front of aluminum sulfide. So we could write this as an equality that says for every 3 moles of sulfur equals 8 moles of aluminum sulfide. So since we're starting with moles of sulfur in our train track here, on the bottom goes the sulfur, and on top, aluminum sulfide. So now we have moles of aluminum sulfide. The next step is mass. So to go from moles to mass, we need to multiply by the molar mass. So here the grams would go on top, and the moles would go on the bottom. So now everything on top you multiply, you divide by everything on the bottom. And we get 14.1 grams of aluminum sulfide. And so the amount of product produced by the limiting reactant is the theoretical yield. So if you were to do this reaction perfectly, this is the maximum amount of product that you can form based on the amounts of reactants given to us.
I have a question.
One second.
Oh, sorry.
Yeah. So there was a typo earlier. It should have been 150 grams here instead of 27. So the theoretical yield was 78.1 grams of aluminum sulfide. We'll look at one more example involving excess reactants. So here we want to calculate the mass of hydrogen produced when 25 grams of water reacts with excess B2H6. So this means that the water is the limiting reactant. So it's going to get all used up in this reaction because there's more than enough B2H6 to react with all the water. So again, what we're going to do is we're going to take the mass of hydrogen, or excuse me, the mass of H2O, convert it to moles of H2O, and then we're going to go to moles of H2, mass of H2. So we're doing the same process we did on the previous example. So now we'll draw our train track. And so again, it gave us the balanced equation, and one of the reactants was in excess. So here we have 25 grams of H2O. Now the first thing, we need to convert it to moles of H2O, so we're going to divide by the molar mass. So the 18 grams goes on the bottom. The 1 mole goes on top. Step 2, we need to convert from moles of water to moles of H2. And we got to look at the coefficients in the balanced chemical equation. 3 moles of H2O give us 3 moles of hydrogen. So if we write this as an equality, we got 3 moles of H2O equals 3 moles of H2. So since we're starting with water, water goes on the bottom in the conversion to moles of hydrogen, and hydrogen goes on top. Now we've done the second step, we've converted to moles of H2. Then we're going to multiply by the molar mass. And here it's 2 grams of H2 per 1 mole of H2. Again, pretty much the similar setup as earlier. We convert mass to moles by division. Then we convert moles of water to moles of hydrogen by the mole ratio, 3 to 3. And then once we get the moles of hydrogen, we multiply by the molar mass to get the mass of hydrogen. So now you multiply what's on top, divide by what's on the bottom. And I get 2.78 grams of hydrogen. And so this is referred to as the theoretical yield. So this is the maximum amount of product that can be produced, or hydrogen that can be produced from these reaction conditions. So here we have this problem where we have the mass. We want to know the mass of aluminum sulfide that is produced when 85 grams of aluminum reacts with 130 grams of sulfur. And it gives us the molar masses of aluminum, sulfur, aluminum sulfide, and also the balanced chemical equation. Oops. And so what you'll notice here that is different from the previous examples is that we have the mass of aluminum and we have the mass of sulfur given to us. So the first thing we have to do is to determine which reactant is consumed up. And the way we do that is to determine which reactant produces the fewer moles of product. So just like we did on the previous 2 examples, now we're going to do a duplicate set of calculations, one for aluminum and one for sulfur, to see which one produces the fewer moles of sulfur. Once we know that, then we can calculate the theoretical yield of aluminum sulfide. And so again, we're going to do one set of calculations for aluminum and one set of calculations for sulfur. And again, it's the same thing. We're going to convert mass to moles, moles to moles of product, and then moles of product. We'll stop there, and we'll do the same for both reactants to see which one produces the fewer moles of product. So we set up our train tracks. So it's going to have one less train track in this one. So again, we're stopping at moles to see which one produces the fewer moles. So we start with aluminum. We have 85 grams of aluminum. We're going to convert it to moles by dividing by the molar mass. Now the mole ratio here is 16 moles of aluminum gives us 8 moles of aluminum sulfide. So we can write that as a equality. So 16 moles of aluminum equals 8. So since we're starting with aluminum, it's going to go on the bottom. And aluminum sulfide goes on top. And now we're going to do the exact same thing for sulfur. For sulfur, we have 130 grams. Again, we're going to divide by the molar mass to get the moles. And here the mole ratio, there's a 3 in front of sulfur, so 3 moles of S8 equals 8 moles Al2S3. So since we're starting with sulfur, it goes on the bottom. And aluminum sulfide goes on top. So now we can calculate the amount of moles of product produced by each reactant. And so you see here that sulfur produces the fewer moles of product. So sulfur is our limiting reactant. So what that means is that we can disregard aluminum. Aluminum is the excess reactant. So then what we're going to do is we're going to convert the moles of aluminum sulfide into mass. So we're going to multiply by its molar mass. We get 202.5 grams of aluminum sulfide. So again, this is called the theoretical yield. Now, before we move on to the problem, let me continue with this problem since someone had asked about excess reagent. And now let's calculate how much excess aluminum is left over. So initially, we started with 85 grams of aluminum. So this was how much aluminum we initially started with. We did use some aluminum, but we want to know how much aluminum is left over. So what we're going to do this, to find how much aluminum is left over, is we're going to take the moles of aluminum sulfide produced by the limiting reactant, and we're going to convert it to moles of aluminum. So when I set up my train track, we're going to go from moles of aluminum sulfide to moles of aluminum and then to mass of aluminum. This will tell us how much aluminum was used. So we start with 1.35 moles of aluminum sulfide. We want to convert it to moles of aluminum. So the mole, for our mole ratio, aluminum sulfide goes on the bottom. And aluminum goes on top. Now we convert it to mass of aluminum. And this is, again, will tell us how much aluminum was used. So we do this. And again, when you calculate how much is used, it should be less than how much you started with. If it's not, something is wrong. And so I get 72.9 grams of aluminum is used. We initially started with 85 grams. So to get how much is in excess, it's just the initial minus the used. And we get 12.1 grams of aluminum is in excess. So once you do this reaction, you won't have enough aluminum to do another reaction of this. And so this is how much aluminum is left over. So it's the excess reactant. So in this combustion reaction, we want to know what's the mass of CO2 is produced when 80 grams of oxygen reacts with 150 grams of propane. So again, we're going to be doing duplicate calculations. We're going to be doing one for oxygen, how many moles of CO2 is produced by oxygen, and how many moles of C3H8 are produced by, or how many moles of CO2 are produced by C3H8 propane. So again, we'll set it up. So we're going to do one for oxygen and one for propane. So we get our train track. So for oxygen, we're starting with 80 grams. The first step is we want to convert it to moles, so we divide by the molar mass. Then we want to do the mole ratio. So here you'll notice a 5 in front of oxygen, a 3 in front of CO2. So 5 moles of oxygen equals 3 moles of CO2. So the 5 moles goes on the bottom because it's oxygen. And the reason we know it goes on the bottom because in the top left of this train track, O2 is on top. So in the mole ratio, O2 has to be on the bottom. And then we have 3 moles CO2. We do the same thing with propane. We start with 150 grams. We convert it to moles. Now the mole ratio between propane and CO2 is 1 mole of propane gives us 3 moles of CO2. So since we're starting with propane in the top left, it goes on the bottom in the mole ratio. And CO2 goes on top. So now we can see which one produced the fewer moles of product. This is 1.5. So here you'll see that oxygen is the limiting reactant because it produces a fewer moles of product. So now we're going to take the moles of product produced by oxygen and convert it to mass. And so this is the theoretical yield of CO2. So the last bit of stoichiometry that we need to talk about is the percent yield. And so the percent yield kind of gives you an idea of how well you perform the reaction. So the closer the percent yield is to 100, the better you perform the reaction. So you got what you did from the experiment was close to what you calculated. And so when we're doing the percent yield, we're comparing the actual yield, which is what you do in the lab or in an experiment, how much you actually obtain from doing the experiment, compared to the theoretical yield, which is what you calculate based on the limiting reagent. So the percent yield kind of gauges how well you did. So for example, for most well-known reactions, a percent yield of say 70 to 100% is very good. You won't get 100%, but you'll get maybe 99%. But the closer you get to the 100, the better you did. Now, one thing you should keep in mind is if you go over 100%, and this happens mainly if you're doing an actual experiment in the lab, on textbook problems, typically they're always going to be less than 100%. But if you're doing this experiment in the lab and you get over 100% yield, that should be a red flag, and try to think of what happened that caused you to have more mass than what you calculated. Because that means you're violating the conservation of mass. And so the theoretical yield we obtain by calculating the yield based on the limiting reagent. The actual yield is going, especially in textbook problems, is going to be given to you in the problem. So to say we actually produced this much of this product. And so here, the theoretical yield was determined to be 1.352. Actual yield is 1.279. So all you do is you do actual over theoretical times 100. Now here we get 94.6%. So again, I would say the majority of your time, your percent yield, especially in textbook problems, should be less than 100%. So if you did a problem and you got over 100%, first thing I would recommend is checking your calculations. So now we'll look at some examples with percent yield. So here we have the same combustion reaction again, but we have different amounts of reactants and products. We have 350 grams of O2 and 650 grams of propane produces 850 grams of water. What is the percent yield of the reaction and how much excess reactant is left over? So first off, this 850 grams of water is the actual yield. So since it's the actual yield, we're not going to worry about that right now until we find the theoretical yield. So you're not going to use the actual yield until we're ready to calculate the percent yield. So now what we're going to do is we're going to determine which reactant produces the fewer moles of product. So we're going to look at O2 and propane. Set up our train tracks. So our mole ratio for O2 to H2O, 5 moles of O2 equals 4 moles of H2O. And for propane, 1 mole of propane equals 4 moles H2O. So we start with the mass of H2O, or O2, sorry. Since we have mass, we're going to divide by the molar mass to get moles. Now, since we're starting with, since we have moles of O2 in the top left, on our mole ratio, O2 is going to go on the bottom. And water is going to go on top. Do the same thing for propane. Start with its mass. Divide by the molar mass. Now the mole ratio here is 1 to 4. Since we're starting with propane in the top left to our empty train track, we're going to put propane on the bottom and water on top. So now let's see which one produced the fewer moles of product. And so by a big difference, oxygen is the limiting reactant. So now we're going to take the moles of water produced by the limiting reactant and convert it to grams. And again, we can disregard everything for propane. So we don't need any of that information now. So to convert moles to mass, we need to multiply by the molar mass. And if we did it correctly, the theoretical yield should be greater than the actual yield that was given to us in the problem. Must have made a typo. So the theoretical yield is 157.5 grams of water. So it shouldn't have been 850, it should have been 85. That was a typo on my part. So again, this is the theoretical yield. Now the percent yield is the actual over the theoretical times 100. So 85 divided by 157.5 times 100. And make sure you times it by 100. Sometimes students will just put the decimal, and that's not percent yield because it hasn't been multiplied by 100. So we get 54%. Usually with percent yields, writing it to the tens place will suffice. So that's the percent yield. But the second part question asks how much of the excess reagent is left over. So O2 was the limiting reagent. Propane was the excess reagent. So we're going to take the moles of water produced by the limiting reagent and see how much of the excess reagent was used. Because initially we started with 650 grams of propane. That's our initial. So we want to see how much we use. So we're going to take the moles of water and see how many grams of propane we use. So now since we have moles of water, we need to calculate the moles of propane. So again, since water is in the top left to our empty train track, in the mole ratio, water goes on the bottom and propane goes on top. Then we convert that to mass by multiplying by the molar mass. And again, this is going to tell us how much was used. We get 96.2 grams of propane was used. And we initially started with 650. So excess would equal 650 minus 96.2. Get 553. And this is how much is in excess. That's how much propane is left over from this experiment. So we'll look at one more example of percent yield, and then I have another problem which is a little bit of a derivation off the normal percent yield problem after this one. So here we have this reaction with B2H6 and water that produce hydrogen gas and boric acid. We want to know what's the percent yield of a reaction that produces 18 grams of hydrogen when we use 40 grams of B2H6 and 90 grams of water. So this 18 grams of hydrogen is the actual yield. So right now we're just going to leave it to the side, and we'll come back to it after we determine the theoretical yield. And then it wants to know how much of the excess reactant is left. So again, we're going to set up two sets of calculations, one for B2H6 and one for H2O. So the mole ratio for B2H6 is 1 mole of B2H6 equals 3 moles of hydrogen. And then for water, 3 moles of water equal 3 moles of H2. So we have 40 grams of B2H6. First step, we're going to convert to moles. Now since we have moles of B2H6 in our mole ratio, B2H6 goes on the bottom. and hydrogen goes on top. Do the same thing for water. Convert it to moles. And then since water's in the top left, for the mole ratio, water goes on the bottom and hydrogen goes on top. So we get the same thing for water. So here we notice that B2H6 is the limiting reactant. It produces a fewer moles of product. So we can disregard the stuff from H2O. Now we're going to convert this to mass to get to theoretical yield. And we get 8 point. Man, I really. Oh no, that's not right. Erase that. .7. No, I was right. So let me change the actual yield because I made another typo here. We'll put a point there, make it 1.8. So now to get the percent yield, equals actual over theoretical times 100. .7%. Now to find the excess reactant, so here water is in excess. So we're going to see how much water was actually used. And then we can subtract it from the initial amount of water. So again, the moles of H2 go on the bottom when we're converting to water. And then we multiply it by its molar mass. This is going to tell us how much water was used. So that's how much water was used, and then we initially started with 90 grams. So the difference between the two will tell us how much is left over, or excess. that's how much is in excess of water. And the percent yield. Second. And so in this problem, we have a reaction below that has a 73% yield. If 72 grams of chromium 3 oxide reacts with 35 grams of aluminum, what is the actual yield of chromium for the reaction? So we have this balanced chemical equation. It states that the percent yield based on the experimental procedure given is 73%. So we start with these amounts of reactants. What's the actual yield of chromium? So what we have to remember is percent yield equals actual divided by theoretical times 100. And so what we're given here is we're given the percent yield. So if we want to find actual equals percent yield times theoretical divided by 100. So if we know the percent yield, we know the theoretical yield, we can determine the actual yield. So now what we need to do is determine the theoretical yield so that we can determine the actual yield. Because it's already given us the percent yield. So again, we're going to set up two sets of reactions, or two sets of calculations, one for aluminum and one for chromium 3 oxide. And typically actual yield is given in grams because you can't use a balance to measure moles. So we have 35 grams of aluminum divided by its molar mass. Now here the mole ratio is 2 moles of aluminum equals 2 moles of chromium. And we get 1.30. Do the same thing for chromium 3 oxide. Divide by its molar mass. Now here the mole ratio is 1 mole of chromium 3 oxide equals 2 moles of chromium. At 0.947. So here we see that chromium 3 oxide is the limiting reactant because it produces the fewer moles of product. So we can disregard the information from aluminum. Now we're going to convert this to mass. And we get 49.2 grams of chromium. And again, this is the theoretical yield. So now we have the theoretical yield, we have the percent yield, we can calculate the actual yield. Basically, we're taking 73% of 49.2. And we get 35.9 grams of chromium. So that would be the actual yield based on the fact that this reaction gets a 73% yield. So again, we're doing the same steps. For each reactant, we convert them to moles of product, see which one produces the fewer moles of product. In this case, it was chromium 3 oxide. That's our limiting reactant. Then we convert the moles of product produced by the limiting reactant to mass to get our theoretical yield. Now that we have our theoretical yield and our percent yield, we can calculate the actual yield. Just one correction here. The molar mass of chromium is 52. I'd accidentally put 53. But the mass of chromium is still the same. It doesn't change. So on that note, that concludes the lecture on stoichiometry.